So like we talked about, there's actually lots of different notations for lists. And so here are two big notations. There's Prolog, and this is a programming language that's based on logic, and it's super cool. Go ahead and Google it sometime. There's ACL2, and in ACL2 I'm kind of giving you two different notations. This is the quote formal notation, and that's the one that uses just the absolute fewest number of built-ins. And there's kind of a shorthand notation, which is kind of the accepted way of doing things. So we have the empty list. Okay, in Prolog it's just square bracket, close square bracket. In ACL2 is nil, and the formal notation is also nil. Okay, now here's a list containing just one element, A, and here's the way we do that in ACL2. We use parentheses instead of square brackets, and don't forget the quote. And the quote is what tells the ACL2 to just treat those as being a list as opposed to a function call. Okay, and I notice that when I write this notation, what I'm really doing is I'm doing cons a nil. Okay, now a needs to be quoted, otherwise it thinks it's the variable a, right? And I actually just mean the letter a, so I need to cons quote a with nil. Okay, now here's a list that contains two elements, a and b. In Prolog is square brackets and commas. In ACL2 it's parentheses and spaces, no commas. And again, it's quoted, quote a, b, otherwise it thinks is the function a that's being called. And the way that we do that in the formal notation is cons a, quoted, because I want the letter a, not the variable a. And I need to const that with a list. And the list that I const it with is the cons b, again quoted, because it's the letter b, with nil. So that is a list that contains a and b. You know, it's a in front of the list that just has b on it. Okay, this is the notation in Prolog when you have an element followed by a list. Okay, and the way we do that in ACL2 is actually with cons. That really is the formal notation, right? Cons is just a way of putting an element in front of a list. Prolog, we have here three elements, A, B, and C. We can do that in ACL2 using the list function. And the list function takes three arguments. Again, I want the letters A, B, and C, not the variables A, B, and C, so all those need to be quoted. And the formal notation is that what I'm doing is I'm consing A to the list, which is created by consing B to the list, which is created by consing C to the empty list, right? And again, A, B, and C are quoted, right? And then there's kind of a mixed notation right here where you have two elements, right? And then the vertical bar saying, and then followed by this. So this is A and B followed by a whole bunch of stuff. We can actually do that in ACL2, although to be honest, I only found out that you could do this when I was looking at stuff for this class. I mean, this is something that I never used, and I've been using ACL2 since, well, since a very long time. So what we have here is list star, and then you give the elements, and then the very last argument has to be a list. Okay? This is the way that I've always done it, which is the formal notation. Cons A to the list that you get by consing B to the list L. Okay, but anyway, don't get hung up in notation. I mean, that's really the whole point of this. Is there's the idea of lists, either an empty list or is an element in front followed by a list. So that's important. Okay, so that's exactly what a list is, right? Either nil, which is the empty list, or cons AL, where A is an element and L is a list. Now, you can define data types in ACL2 using def data, okay? And def data is really useful when you're trying to specify either a new data structure, right, like a tree of numbers or a list of numbers. And we're going to see that it's actually really important to have the right types when you're doing something for random testing. So for example, if I'm trying to do a little theory to show that some function works correctly, but I'm expecting that function to be accept a list of positive integers, then I actually want to define the type list of positive integers. Okay, so here we have a list of naturals. And we say def data, this is the name of the type, okay? LON, that's actually supposed to stand for list of naturals, okay? And here's a keyword, right? One of, so it is either nil or, right? That's what one of means, right? So it's either nil, which is just a constant, or it is cons of a natural onto a list of numbers, Okay, so notice that this is a inductively defined type because it's a type that's defined using itself, right? Just like lists, right? And this follows the pattern for lists. So I can now define what it means to be a list of naturals in ACL2. Okay, so what exactly does that do? Well, it lets me define this, right? So the kind of the important things here are LON, which is the name of the type we're defining, list of naturals, and then nat, which is the name of the type of natural numbers. Okay, and we're taking advantage of just nil, which is a constant, and const, which is a constant function. Okay, now once you define this, it actually builds a few things for you. The one that you really need to know that it's building is this function ln p. And notice what it does. It just takes ln, or whatever name you give to your data type, and it has a p on the end. That's actually a pretty common thing in Lisp and ACL2, and that is that functions that are return booleans, true or false, okay, are called predicates. And you're familiar with that, right? A predicate is something that returns true and false. Because they're predicates, they have a p at the end of the name. So we've seen cons p, right, which means is this a non-empty list? We've seen nat p, which says is this a natural number? We've seen integer p, right? Is this thing an integer? And here is ln p. Is this thing a ln, which is defined using this equation here, right? So ln p of quote 1, 2, 3, 4 is actually true because that is in fact the list of natural numbers, whereas ln p of 1, 2, ab is false because a and b are not natural numbers. Ln p of 1 is false because it's not a list, right? Be careful with that one, right? Some people think, oh, of course, that's a list of one element. No, it isn't. Okay? All right. What exactly does the function ln p look like? I mean, like I said, ACL2 is building it automatically for you, but we might legitimately wonder, what is it? And here's the important facts that you need to know. It's got two equations, right? So one of the equations is the base case, right? And the base case tells us that if the thing that I'm worried about is actually the constant nil, then yes, that is a list of natural numbers, right? And then we have the inductive step. Or that's when I think of it as a proof. I can also think of it as recursive part of the definition, or a recursive equation. Okay, so ln p of something which is a cons of something a followed by l, right? Well, that is actually true if a is a natural p, okay, and l should be a list of naturals, right? So again, ln p is defined recursively. Ln p is defined in terms of itself, and that's not a surprise because what I have is a data type, right, which is defined inductively, right? So here is one of the cases. This is the base case, and that results in this equation. And here's the other case, and notice that the cons is feature right there. That needs to be a natural. That's feature there. That needs to be a list of naturals. That's feature there, right? So it just comes straight from the inductive definition. This is very common. The inductive definition kind of tells us how to write functions that work on that particular data type, and of course that also tells us how to do proofs using that particular data type. Okay, so here is a definition. This is a function that's in the programming assignment. Now let's take a look at that. This is working on S1 and S2. S1 and S2 are lists, okay? Okay, and I'm using the list to represent sets, right? So using abstraction, which is something that comes naturally to us computer folks, right? Using abstraction, then I can look at that and say it's working on sets. That's why I call it S1 and S2. But in the actual, nitty-gritty of programming code, they're really lists, okay? Because that's what ACL2 has. So this is taking the union, right? And what we're doing is defining these kind of two equations, right? So let me make that clear. There are two equations, right? And that means that I need one if statement, right? Because one if statement lets me make a choice between the first equation and the second equation, right? If I have three equations, then I'm going to need two if statements. One lets me decide whether I'm in case 1 or case 2 or 3, and the second one lets me decide whether it was case 2 or case 3. right? So if I have n equations, I'm going to need n minus 1 if statements. So here is the if statement, right? So what I have is the then, and what I have here is the else. Okay. Now, const PS1, that is testing, is it true that S1 is a non-empty list? So non-empty list, that's actually here. This is the then, right? And this here is the else. Right? So now if you look at the value of the expressions, this is simply exactly what you see on the right-hand side of the else case. And the same goes for this part right here. Oops. Okay, this is exactly what you see on the right-hand side of the definition for that for the then part, or that second equation. Okay, now I'm using kind of pattern matching. Okay, so this is a pattern const AS1, but here I don't have a pattern. I just have S1, right? So S1 needs to match const A. And unfortunately, it's the same variable name, right? So I'm just going to call it quotes S1, right? To make a distinction, okay? All right, so what do I need? I need A. What's A? A is actually supposed to be the first element of this, right? So A is actually equal to the first element of S1. That's what you see here, okay? And the other term is set union. Yep, that's right there, of S1 and S2. So what's S1, right? Well, S1, and this is the quoted one, right, because it's part of the pattern match, S1 is just the rest of the variable S1. That's what you see here. Okay, so whenever you see a recursive or inductively defined type, then we can always kind of write functions, okay, using this style, which is by providing a bunch of equations, right? And the equations correspond to distinct cases, right? And often those cases will mimic the inductive definition of the type, okay? And then we can write that in ACL2 by having a bunch of if statements, right? One fewer than the number of cases. And the whole point of the if statements is to decide what case am I in. And then the value that gets returned when you hit to that particular point in the if statement is the right-hand side of the equation. And you're going to need to do a little bit of translating like we did here, okay? Because when we write the equations, we pretty often use pattern matching, okay? So we need to actually take care of the pattern matching because it's not part of ACL2. If you do other functional programming languages like ML, they actually have pattern matching built in, so it's even easier to go from equations to code. Okay. Now imagine we have a function called length, okay? And here are the two equations for length, okay? The length of nil is 0, right? Because the length of an empty nil, of an empty list is 0, right? Length is just the number of elements in the list, okay? Now, length of const AL, well, that should be 1 plus the number of elements in L, right? So 1 plus length of L, okay? Now, I want to go here in the other direction, okay? I want to actually try to write the definition of this function. So length L, and I'm going to call it the list L. Okay, so how does this work? Well, I'm going to have a condition to let me choose between these two rules. So if const P L, right? That's kind of the only condition that I have. Is it an empty list or not? Okay, so if const P L is true, then it means that it's not an empty list. So this is where the true will go. I'll leave some room, and let's take care of the false case. That means it is an empty list. Well, then it's 0, right? That's just because of this. That's the right-hand side of that equation. And then I need as many right parentheses as necessary to close it. This one closes the if, this one closes the definition. Okay. Now, what is the true case, right? Well, if it's actually a non-empty list, then the answer to its length is 1 plus the length of the list, right? And it's the length of everything but the first element, right? Because this is the pattern that I matched. Some element followed by L. So is actually the length of the rest of L. And as many right parentheses as I need. Okay, so that's again just an example of translating equations to ACL2 code. All right. So now a little bit of just plain old intuition, okay? Set union of a list that has n elements and a list that has m elements. What it does is it just puts the elements of the first one and then the elements of the second one. So that's what the union is, right? So now, if you think about what the length of the union of two lists should be, it should be the length of the first list plus the length of the second list, right? I mean, that's obvious, okay? So let's try to prove that.